To invite the next speaker, Wilkinson. He will tell us a bit about register tiling for unstructured sparsity in neural network inference.
Hi everyone, I'm Lucas, and I'm here to present our work, Register Tiling for Unstructured Sparsity and Neural Network Inference. This work is done in collaboration with my co-first author, Kazem Cheshmi, and under the supervision of Maryam Dehnavi. And this work was done while I was a master's student at the University of Toronto. So it's no surprise that neural networks are everywhere these days, and with that comes a desire to make them both smaller and more efficient. And one method targeting this is pruning. And the basic idea behind pruning is to remove connections that don't contribute meaningfully to the accuracy of the network. So here, for example, we have in the red, we have a dense network, and in the green, we have the equivalent pruned network. And so we can see that in the green box, we have the unnecessary connections removed. So there's been pretty good advancements in pruning in recent years, which means we can prune many common models with minimal loss in accuracy. And this is good because it theoretically reduces the model size as well as the amount of compute required. However, in practice, realizing these reductions is very challenging, as the connections that remain are highly unstructured, making these models difficult to optimize. So just stepping back a little bit, when we're doing neural network inference, we actually lower these down to linear algebra routines. So here, for this fully connected layer, we have an activation vector that gets multiplied by a weight matrix. However, in practice, our activations are almost always matrices as well, and this comes from the batching of multiple inputs at the same time, or in more modern architectures like transformers, processing many tokens at the same time. This means that our neural network inference gets dominated by matrix-matrix multiplies. And in the prune case, this actually becomes a sparse matrix multiply, where we have a sparse weight matrix A, where the zeros represent connections that have been removed, getting multiplied by a dense activation matrix B, resulting in a dense activation matrix C, also known as SpMM. So when it comes to optimizing any kind of matrix multiplication, the key challenge is to adapt it to the memory hierarchy of your device. And so here we have a memory hierarchy for a fictitious CPU, where we have DRAM all the way at the bottom, and at the top we have our FMA, or compute units, that perform the fuse multiply adds that make up our matrix multiplication. So here I'm just going to use lowercase letters to represent individual values of each respective matrix. And these values initially start in DRAM and have to be moved all the way up the hierarchy into the FMA units where the fuse multiply add can be performed. Ideally, we want to reuse values at the highest level of the cache possible. So if these values were already in L1, then we can greatly shorten this trip and we can speed up our code overall. In the ideal case, these values are already in the register file, and some reset at this level is required to reach peak performance on almost all machines. The challenge here is that as we move up this hierarchy, the memory sizes become smaller, and so at some point our problem doesn't fit. Luckily, as a community, we do have a solution for this, which is tiling. So just a quick background on tiling. So if we start with our full problem in DRAM, instead of trying to compute it all at once, we'll instead grab a small subproblem that can fit into cache and instead work on this. And this can be done recursively such that we can get an even smaller problem that then fits in the register file. And this level is the focus of this work. So zooming in here, we can see that this problem ends up being a small partial, an outer product between a small column vector of A times a small row vector of B, accumulating into a 2D tile of C. And since this is in the register file, we have to allocate these values at C, A, and B into the registers at compile time. And this is because registers are not runtime addressable, and so the compiler needs to know which registers are involved in each FMA operation. Looking at the code here, this is quite challenging. So typically, the author of the code or the compiler will perform an unroll-and-jam in order to fully unroll those loops to result in code that looks like this. And with this code, now register allocation is pretty straightforward, and this is an example allocation. But if we continue to look at this code a little bit more closely, we can see here that these first two operations involve the first row of C and A. These next two operations involve the next row of C and A, and so on. And the reason I bring this up is because what we're concerned with is a pruned neural network or a sparse A matrix, in which case some of the values will be 0, and we ideally want to skip the operations involving those zeros. So for example, with this A tile, if this middle value was 0, then we ideally want to skip these middle two operations. Same goes for the first value, and so on. So as you can kind of already start to tell, we end up with many versions of this unrolled loop. And in fact, the number of possible patterns for this A tile kind of grows exponentially with the height of that tile. And so ideally, we don't want to generate code for each of these cases, since that could quickly exceed our instruction cache or cause too much branching overall. So we want to kind of try to find a way to reduce the number of codes we actually generate. And so if we take a look at two of these patterns, we can kind of see that there's some similarity here. So in both these cases, we actually perform the middle two operations, but in the blue case, we continue on to perform the last two operations, whereas in the red case, we skip this. But we don't actually have to skip these operations. Since they're multiplied by 0, they won't change the result, and we can still compute them. It's just going to be wasted work. But if we're willing to make that trade-off of additional wasted work, we can now jam these two codes into a single code that can execute both. So going back to our original set, here we can see that we've now reduced the number of patterns we need to generate code for by 1 at the cost of this redundant computation represented by the striped pattern in the case of the red tile. But we still have this open question of what to do with the rest of the patterns. There's still many patterns there, and we're still generating a lot of code. So if we look at these two on the right, we can kind of get an intuition about what patterns would be good to combine. So this would probably be bad, because we can see here, represented by the striped patterns, we're introducing redundant computation in both cases. Going back to our original set of the blue and the red, could be good, because in the blue case, we are performing no redundant computation, but in the red case, we're performing 50% redundant computation. And so whether this is good or bad kind of depends on how frequently that red case is running in comparison to the blue case, or just generally in comparison to all the other cases overall. So for example, if that red case is running 100 times for every 1 time that blue case runs, this is probably not a good candidate to be jammed together. So instead, we would likely want to specialize code for that red case, such that there's no redundant computation happening there, and instead take the blue case and jam it with a more frequent tile. And these frequencies can actually just be extracted ahead of time from our set of target matrices and kind of averaged to give our code generation a bit of a sense of our target matrices. So just to formalize this a little bit more, here we have our set of all possible patterns this A tile could take, and we will call this set E, and we're trying to map it to the set of patterns we actually want to generate code for, or set R. So this is an example solution where we've mapped every element of E to an element of R. But instead of thinking of this as mapping individual elements of E to elements of R, we can instead think of this as mapping subsets of E to elements of R. And using this formulation, we can, or this view of the problem, we can then formulate it as a minimum weighted set cover problem, where here G is our universe of all the possible subsets of E. And then we're trying to minimize the cost of the selected subsets. This cost function is a little bit more complicated, but in this talk, I just want to focus on one of the terms specifically, and that's this frequency term. And this is what gives the cost model an idea of how much redundant computation it's introducing by selecting the subset. And that uses that frequency information that we extract from our target matrices. So just to complete the formalization a little bit, or the formulation of this minimum weighted set cover, we do need some additional constraints. So the first constraint is just a basic covering constraint that ensures all the required operations in E are covered. And the next constraint, we use estimates of the code size for the patterns in R and a hard code size limit to ensure that we never exceed the instruction cache. So just to kind of give an overview of what we covered so far, we initially enumerate all the possible patterns that this A tile could take before moving on to solving our minimum weight set cover to get a mapping from E to R using frequency information we've profiled from our target matrices. And then we move on to code generation. So if this is the sparse outer product we were trying to unroll inside of the full matrix multiplication, then we can now replace this with this switch, where this lookup table represents the solution to our minimum weighted set cover problem, or our mapping E to R, and it tells us to which element of R to jump to, and these are the generated cases here. Although this code still has some performance issues or complications, and that's because it's actually inside of this inner K loop. And so visually, this K loop kind of looks something like this, and this is really bad for the branch predictor and comparisons overall, because on every iteration, we're jumping to one of these generated cases. So instead, we transform it into something that looks a little bit more like this, which where we iterate over all the iterations that involve the first generated case before moving on to the next, and so on. And this is much more friendly to the branch predictor, because on each iteration, we're either continuing with the same pattern or moving on to the next, unlike in the last case where we could randomly jump to one of those 4 patterns. So from a code perspective, that looks like taking this code that we have here and transforming it into something that looks a little bit more like this. However, now we need to know which iterations of K belong to each of those cases. And so that's where we use this AI-AK data structure, which is pre-populated by a scheduler. This means that our final SpMM code actually has this scheduler executor decomposition, which is actually particularly well suited for neural network inference, as our A matrix is static. So the scheduler code only needs to be run once, and during inferencing, we only need to run the executor code. This means our overall flow ends up looking like this. With this code transformation here, we coin Unroll-and-sparse-jam. So moving on to experimental results, here we have the results for our 784 by 784 80% sparse matrix. And on the y-axis, we have our execution time. So in this case, lower is better. And on the x-axis, we have loads per FMA, which is just a bit of a measure of how efficient our register tiling is. It tells us how much traffic we have between L1 and the register file per unit of compute. So in this case, lower is better, as we want to be having less traffic per compute unit. So compared to the our sparse baselines, we can see here that our loads per FMA is lower. This means our register tiling is more efficient, and as a result, we have a lower execution time. Compared to our dense competitor, here we can see that while dense can actually have a very efficient register tiling, they perform more compute overall, and that's represented by the size of the bubble. So we perform less compute, also resulting in lower execution time. We tested our method on over 2,000 matrices from the deep learning matrix collection in the sparsity range of 60 to 95%. And here on the right, we can see that compared to the sparse competitors, we can consistently outperform them across the sparsity range tested. And this also goes for our dense competitor, MKL SpMM. We also went on to integrate our method into XNMPack, a mobile inference engine, replacing their SpMM with our own, and running it on a Raspberry Pi 4 for a MobileNet V1. And here we can see for 70, 80, and 90% sparse, we were able to see latency improvements across the board. So that concludes my talk today. So just in conclusion, we created a state-of-the-art SpMM by mixing compile time techniques with runtime techniques and a little bit of inspection. And we do this through a novel Unroll-and-sparse-jam code transformation. So thanks for your time, and I'm happy to take any questions.
Any questions?
Hi, I'm just curious as to how many different versions of the tiles you ended up creating for your benchmarks.
Yeah, so we did test two different T sizes. So we did a T of 4 and a T of 8. And so for both of those, we ended up with a few different options. But generally for a T of 8, we ended up with about 42 codes being generated. And for a T of 4, we ended up with like 9 to the full 16 being generated. Yeah.
Okay. And I guess there's also the parameter of how many different tiles you want to allow, right? Or is that something that is automatically inferred?
So that's restricted by the code size. So that code size constraint takes into account how big the generated cases are going to be, and then if you have a bunch of small ones, then yeah, you could have a few more patterns that you generate, but if you have large patterns, then you can generate less. So that's generally handled by that, yeah.
Oh, thank you.
Mm-hmm.
Any other questions? All right, we're ahead of schedule, so I have time for a question of my own. So you said that all the scheduling part is done as part of the code generation, so it means it's totally static, right?
So our code generation generates a scheduler that you can then use to produce a schedule for whatever matrix you have to run. So you could set your set of target matrices to be your entire model and generate a single kernel for that, and then for each specific layer, you can run the scheduler that gets generated and get the specific schedule for that specific layer, and then during inferencing, you just run the executors using those pre-computed schedules. So the scheduler kind of fits in this almost model compilation time, which is kind of in between like the actual code compilation and the inferencing, where you're kind of just setting up the model or loading your weights. You can run that scheduler at that time.
So you assume you have access to the input and essentially all of the input, so you can generate the schedule, right?
Just the weights of the model, not the input, because the input would
yeah,
be
not the input, like the size of the input, for example.
Yeah.
Okay, so my question is in large language models, what's been very useful for distributing the computation is having these inputs that are padded. You can sort of clip them, and then you have these different sizes, and you can sort of split all the data into different sizes and send each size bucket to a different GPU. So I'm wondering how would your system adapt to something like that? And I'm kind of leading to, did you consider doing some kind of a dynamic scheduling like later in the phase, later in the computation?
Yeah, sorry, I was having a little bit of trouble hearing, but I'll try my best. So basically, since we're operating at the register tile level, our code actually lives inside of cache tiles, which is typically where you'll do that kind of level of parallelism, where you're distributing across GPUs. So you can take a cache tile, and then you can apply our method to just that broad cache tile. So yeah, we don't deal with parallelism specifically in the patterns, but instead at the cache tile level, we deal with our parallelism.
Got it, okay, thank you very much. All right, let's take the speaker.